Okay, we are live.
Hello, everybody.
So, hi everybody. Thank you for joining us in this webinar about design automation for structural brackets. So, I am Gregorio Carazi, product manager of cognitive design. So, I will show you today how to use cognitive design to solve some engineering challenges that we face with, in this case, bracket design. And I'm here today with Henri de Charnassé, which is the CTO and co-founder of Cognitive Design Systems.
Hello, everybody. So I'm Henri de Charnassé, and today I will show you the recent advances we've done with AI.
So let's have a quick look at the agenda of today. So we will do a quick introduction of cognitive design systems. And then I will show you the use case on structural bracket design automation and how also we can use cognitive design to solve those problems. So I will show you how to do it directly into cognitive design. And then we will show you a brief introduction of what we are looking at in AI orchestration of those kind of workflows using Claude LLM. And then we will conclude with a Q&A session. So let's start from the introduction.
Yes, and quick word before introduction. So don't hesitate to ask questions in the Q&A channel, and we will answer them as we go. All right, so Cognitive Design Systems were created in 2021, on this day actually, 10th of March. So yeah, 5 years ago already. We are 20 people. We did 2 million euros fundraising in 2023, and we have customers all around the world. Yeah, many of you are already here. So, vision of the software, it's to transform engineering into a cognitive creation. So what that means is we empower the designer. We give him insights on simulation, on manufacturability, on costing, on sustainability, to do some better designs. So thanks to this, we can break the silos. The designer don't need to do back and forth between departments to have the information he needs. And we do a lot of automation in order to to automate the boring work. So the designer don't spend his time pushing some buttons, right? He spend his time doing some actual engineering, answering some questions and finding the best way to design a part. So to do this, we have three main technology pillars. The first one on the left, implicit modeling. So this is a really robust way to design some parts using some distance fields. It's a volumetric-based approach, and it allows to, because it like literally doesn't break, it is really prone for, really good for automation. So because the geometry doesn't break, we can do some automated operations to improve the manufacturability of a part, to post-process topology optimization, without having the user to actually draw and do some fine-tuning on the parts. Second one on the top, parametric design. So this is really useful because you just need to actually provide your requirements to do design, right? And the parametric approach is either to do some iterations, so you can relaunch the calculation with different parameters, different processes. So for example, you've made a part in molding and you want to see how it would look like in machining. So it's possible with that parametric approach. And it's also really great to reuse the workflows. So Gregorio will present this during the live demo, but you can use the same workflows on totally new parts and apply the same methodology. And the third technology pillar on the right, it's the data-driven approach. So we provide a lot of insights directly to the designer. So as I said before, we give access to some costing KPIs, for example, some manufacturability insights also. So will my part be produced well or not? Where would be the problems? and of course on performance simulation and on sustainability because it's becoming bigger and bigger. So yeah. And today you will see the new version of cognitive design that we've released a couple of months ago, where we've added pretty huge feature, which we call the Design Explorer. So as many of you may already know, we use blocks. So you can see on the image on the left to design parts. And the new view that we've added is the dashboard on the right, where you can track your design iterations. So as you design, you can save them and get access to a lot of KPIs. And then what's really good with this is you can compare afterwards your parts. So you can use the graph or some filters to find out the best part for your requirements. So maybe you want a part that is a bit heavier but cheaper, for example. So you can use this to do this kind of study. And then you can bring back the workflow in the canvas to do some final touches on the design.
Okay, so thank you, Henri. So let's look at the use case of today's webinar. So we will be working on two brackets that have quite a different geometry and also different dimension. So why brackets? Because it's one of the most design and redesign part category, and you can find bracket pretty much in every industry. You can find them in automotive, aerospace, or also industrial machinery. So it's quite common to work on brackets several times during the year. And it might seem easy, but in fact, this kind of part have a lot of competing constraints. So they need to be stiff but very light, and they have to be as much optimized as possible and as much cheap as possible, but also manufacturable and reliable. So it's not so trivial, and most of the time engineers will look at cost performance trade-offs and then go back in a second time because maybe some manufacturing constraints were not taken into account. Another challenge we face when redesign several bracket components is also that once we did a workflow for one bracket, we usually start from almost from scratch for other brackets, so we lose a lot of time, and there's little time actually left for innovation or optimization. So let's also look at what will be the targets of this example use case. So I will fix the material. I choose the aluminum alloy, but we can explore different kind of processes, so additive manufacturing, die casting, and CNC machining. Our main objective, obviously, will be to reduce the weight of the original bracket at least under 30 grams for the first bracket and under 2.5 kilos for the second one. And we will look at the safety factor to choose to see if our structural requirements are met. So the first bracket, let's say it's in a less demanding environment, so a safety factor of higher than 1.3 is enough in this case. And let's say that the second bracket is in a much more demanding environment, so we need a safety factor higher than 3, for example. We will also look at the displacement because we want a certain stiffness. So for the first bracket, we want to be under 0.15 millimeter, and for the second one, we want to be under 1 millimeter. And for this, in this scenario, we have only one load case. is only a bending load case that is applied on the central hole for the first bracket and on the 3 front holes for the second one, but I will show you a little bit better during the demo what are the functional regions I used. And the objectives will be to basically answer the engineering challenges. So we will need to quickly perform a cost, performance, and manufacturing trade-off. We want to automate as much as possible, reuse as much as possible the workflow we have already done for the first bracket, for example. And obviously, we need to achieve the specification targets while meeting the structural requirements. And I will show you that all of this is possible with cognitive design. And just before showing you the workflow, I want to talk a little bit about the different approach and methodology we want to introduce with cognitive design. So when you design a bracket in the actual the legacy workflow, let's say, you will go. It will be quite linear. So you have the requirements for your first bracket. You will do a first CAD model, some kind of optimization. Then you will do simulation, manufacturability analysis. And most of the time, you will do several loops between simulation and manufacturability. So let's say for the example that you take 2 weeks to have a first bracket. The problem with this workflow is that each new bracket, you have new requirements, but you still need to redo the CAD model. You still need to redo simulation manufacturing analysis from scratch. And all brackets will take you more or less the same time. But what you can do with cognitive design is, at least in the phase of design exploration, you can actually reuse the workflow you already set up for the first bracket. So you will have the requirements for the first bracket. You will do all the design exploration and a little bit of fine-tuning with simulation-driven design and manufacturing-driven design on your first bracket. Then you will export the model and still do the validation on your legacy software. And it might take you 2 weeks, let's say, for the first bracket, but all the other brackets you will design afterwards, you can spend a lot less time on the design exploration because you will be able to reuse the first workflow you already did. So in this use case, in the workflow I will show you is divided basically in 3 steps. So the first one is the workflow build-up, where I will set up the design space and or the load case and the simulation setup on the legacy part. I will do a step of generative design with topology optimization, for example. I will refine the geometry with simulation-driven design for performance and manufacturing-driven design for manufacturing. And I will extract KPIs from the simulation, from the manufacturability and cost analysis in order to send them to the design explorer. So in the design explorer, this will be the second phase. You will be able to look at all your iteration that you saved and use filters or look at the graph to quickly perform trade-offs and see which is the most suitable iteration for your requirements. And then I will show you the last phase, which is reuse this complete workflow on that I generate on the first bracket, reuse it on the second bracket. Okay, so let's look at the workflow inside cognitive design. So if you don't know cognitive design is a node-based software. So you will use all those building blocks, all those components, which are each one is related to a specific function. So you will build all your chain of function, and you can compute at the end of this chain to get the result. So all those blocks are organized in the left panel. They are organized in order of appearance in a typical workflow. So from the top, you have the exchange tab, where you have import, export function, and data conversion functions. Then you have a tab for model preparation, where you have select cut faces, select mesh faces, or transform function. Then you have a tab for generative design with topology optimization, topology weaving. I will explain what topology weaving is later. Then you have the tab for simulation and analysis in general. So you have FEA, you have manufacturing analysis, cost and CO2. You have a tab for optimization, simulation-driven design, manufacturing-driven design, lightweighting with lattices, for example. Then you have a tab for shape modeling. You have Boolean operation, offset, shell, or texturing. You have a tab for macro blocks. So I will show you how to create, edit, and save your macro blocks. A tab for more, let's say, advanced functionalities to work on meshes and fields. And then in the end, you have a tab for all our beta functions. So you will find all new functionalities you can try. So in this new version of cognitive design, we also added for project management, you have a project manager. You can have different sub-projects inside the main project. And you also have a media manager to quickly look at imported and generated models and also exported or re-imported inside the canvas. And we have on the right side the Design Explorer panel that I will show you later. So let's look at the workflow. So we start with import and legacy and simulation on legacy model, generative design and structural optimization, design for manufacturing, and then KPI extraction on our each iteration that we send to the Design Explorer. So let's start from the first bracket. So here I import the step file of the first bracket. So as you can see, you have to use this compute block to compute what you have in your chain. Then you have the simulation setup. So here I have my first macro block that I will show you. So here there's the loaded faces and the fixed faces that I will use in my simulation. And all the setup of the simulation is actually stored inside the macro block. You can reuse elsewhere in the workflow or in another workflow. You can save it or edit it. So inside the macro block, on the left side, you have all the inputs that are needed. And here I have my setup of the simulation with the restraint. I have a torque load to simulate a bending load on the central hole of the part. I have one load case and all the parameters for the simulation, like the resolution, for example. So the simulation is very quick because it is meshless, it's powered by intact solutions. So it's very good for design exploration. Here you see the result on the legacy bracket. So we will use those as reference. Von Mises stress and displacement, for example. And then we will extract, also for reference, the KPIs of manufacturing cost and CO2 of the legacy part. So here I have also a macro block for the CO2 and cost. You have different processes. I will start with machining. So you can tune the process settings and the manufacturing analysis parameters. Cost analysis is you can set your recurring cost and non-recurring cost, for example. And in CO2, you have the machine power, material specific energy, source emission factors. You can set up with your values. And once you have saved your macro block, you can use it, reuse it everywhere. So here on the first bracket, you have the manufacturing analysis. So everything seems quite good. And we can send all those information to the Design Explorer. But before going to Design Explorer, we will generate other iterations. So for example, here I did topology optimization. So it's not mandatory, but you can use a different start design. Here, for example, I added holes in X, Y, and Z direction into my design space. Why I did this? Because the topology optimization is level set based, so it's easier to move boundaries when you have when you add holes inside the design space. And yeah, here you have the result of the topology optimization, and you have on the left the parameters I used, so 0.15 volume fraction, and you can also tune the how fast the boundary will move with the strength. And I then ran the simulation on the topology optimization. Here I reused the macro block, and yeah, I can see that there a little bit of stress concentration in those areas. So I can use simulation-driven design, which will take the simulation result, and you have different methodology to use those results to modify the geometry. So here, for example, I will modify the thickness using an offset. So I will add material where the von Mises stress is higher, for example. And here you can see that after this operation, I can lower the von Mises stress. Here you can see a comparison between after the topology optimization and after the simulation-driven design. So this will be our baseline for the manufacturability design. Here we use the manufacturing-driven design. We will start from additive manufacturing. So I will check for minimum thickness and bulk volume. So I will modify the part to avoid thin structures and avoid potential heat accumulation areas. Then I can do the same thing for die casting, where I check for minimum thickness, but also for feature spacing, because I don't want small gaps between features. Otherwise, the mold is not manufacturable. And also I want to fill all undercuts. And then I can do the same thing for machining. So also thickness and feature spacing. But I can also make all areas of the model accessible in for a 3D axis machining, so in X, Y, and Z direction. Now that I have my models that are manufacturable, I can do another pass of simulation and extract the KPIs for manufacturing and the cost and CO2. So let's look, for example, at the results of the manufacturing analysis. For additive manufacturing, in this case, you have minimum thickness, you have supports estimation. You have bulk volume, but in this case, there's not much. You have a little bit of a quick section variation and no internal cavity. So it's pretty good. And once you have all your KPIs, just like we did for the legacy part, you can save this iteration and send it to the Design Explorer. Same thing for die casting. We have thickness variation with respect to an average thickness, minimum thickness check. We have feature spacing check. We have the draft analysis. So here, there's still a little bit to do for the draft and the undercuts analysis. And then same thing for the CNC machining. Here we have minimum thickness and feature spacing. So we have now all the information. So here I show you for one iteration, but I can do, here I use topology optimization, but I did another round of iteration with topology weaving. So the workflow, the general workflow stayed the same. I just swapped the topology optimization with topology weaving. So what is topology weaving is a method, an alternative method to topology optimization, where you connect a functional region while staying inside a design space. And you can use an external simulation result to guide those connections. So you can tune also the thickness of those connections and the wrapping strengths of the envelope. So this is, for example, an example of result using this method. And yeah, all the rest of the workflow stay the same with my simulation design, manufacturing and design, and the KPI export and send to Design Explorer. So now let's look at the Design Explorer. So you can open the side panel and you have a recap of a list of all the iteration you sent to design, you saved in Design Explorer. So you have all the KPI for performance and manufacturing and cost and CO2, and you can play on the graph with the axis to see to quickly find what you are looking for. And for the comparison between the iteration, you can, for example, pin here. I pin the legacy bracket, and all the trends will update to see which iteration is better in which KPI and which KPI is worst, for example. And on the bottom right, you have a little bit more details on all those information and also the scores of each manufacturing analysis we do. You can export this Design Explorer in a PDF file. We have all the recap of the pinned model, the legacy bracket, and all other iteration with all the checks of manufacturability and all the KPIs for simulation and cost and CO2. So you can easily share this information. Now let's find our best candidates. So we will apply, in this case, a filter on safety factor. So for this bracket, I will look at something higher than 1.3. And here you have your candidates. So if you look at the lowest weight, for example, you have an AM iteration, but the cost is higher, and you have a die casting one. So if in this case I want the lowest cost possible, I can choose, for example, the die casting result. And what I can do is also I can compare one by one those iterations. So here, for example, I will export the comparison in PDF between the legacy bracket and this die casting one. So you have on top the position of those iteration on the graph, and on the bottom the direct comparison between the two. And now let's say that I want to export this model to perform the final validation, so I can insert the workflow I used to generate this die casting iteration, for example. So this is, I insert the workflow inside this canvas. So here you can see that I have exactly the model you saw in the Design Explorer, and then we can export as a step file with our mesh2b-rep block. So with our mesh2b-rep block, you can keep the functional region clean. And so as you can see, the more organic parts, in the organic parts you have patches, but on the functional region you have clean surfaces you can easily click on to set up, for example, the validation simulation in your software. So now that we are done with the first bracket, let's look at the second one. So here, what I did is just a save as of the previous workflow is all exactly the same. I just swapped the input bracket model. So this is the second one. And obviously I changed the simulation setup. So I created another macro block for this bracket. And then the rest is pretty much the same. I just play a little bit with the topology optimization. So the start design has holes only in one direction. And here you have the result. Everything else is the same. Here I added the supported holes modification in this case. So you see the holes that have supports are modified. Here you have the die casting result with the undercuts that are filled, and the CNC machining one. So everything pretty much the same as the workflow on the last bracket. And so we can go directly to the Design Explorer and set up this time different filters. So a higher safety factor of 3, and also a different max displacement. For example, here I need something lower than 1 millimeter, and so I can quickly see what are my best candidates. And I still have one additive manufacturing one, which has the lowest weight, and the die casting one, which is which is better in terms of cost. But if, for example, in this application, I don't look at cost is not so important, I could, for example, choose the additive manufacturing one, since I want to reduce the weight as much as possible. And here, the same, you re-import the workflow you used to generate this model, you use the mesh2b-rep block, and you have your step file for the final validation. Okay, so this was the demo of how you can solve those problems inside cognitive design. So what did we do? We achieved with the Design Explorer, we could do a rapid trade-off, and not only between performance and cost, but also with manufacturability insights, and also CO2 insights. So with the graph and the filters, you can easily identify the best candidates. So we achieved 40% of weight reduction while staying within the structural requirements. But most importantly, we had information about the manufacturability, and we could refine the model for manufacturability inside the design exploration loop. And then, so not only we accelerated the workflow for the optimization of the first bracket, but we also greatly accelerated the workflow for the second bracket, since I pretty much reused the same workflow. So you can really focus on optimization. For example, you could spend a little bit more time on topology optimization parameters, for example, because the generation of your workflow will be very quick anyways. Okay, so that's it for the use case in cognitive design. Now Henri will quickly show you what we have been looking into in those past months, and basically AI orchestration of those workflow I showed you with Claude LLM.
Sure. Thank you, Gregorio. Yeah, can you go on to the next slide, please?
Yeah, sorry.
Yeah, so to quickly show you the concept, so we've been experimenting with LLM models to orchestrate cognitive design workflows. And we do this through a pretty standard way, actually. It's called the MCP protocol, Model Context Protocol. So this is used already by LLMs, for example, to allow them to write emails for you or to add some items to Notion, for example. So it's a bridge between a tool. So in that case, it's the backend of cognitive design and the LLM. So the LLM can see which tools it can access and call them like this. So we have a prototype with this. I will be showing it to you right now, and it allows to call directly the cognitive design operations from the LLM, and it allows to do some design works. So it's kind of like you have an engineer with you that is using cognitive design, and you just give him orders, right? You can ask him to do the work. So it's a pretty interesting approach. So I will share my screen. All right. Okay, so for the sake of the demo, I'm going to use Claude Desktop, but it works with any LLM that supports MCP, so it could be on Copilot also, for example. So here, I've got the servers running on my PC. So this is local, by the way, the server. So the actual models and computation stay on your PC, but it's connecting to Claude to give the orders, right? Using cognitive design. So here, for example, can just ask it to create a lattice sphere. And so this is pretty, I would say, vanilla. So in Claude, as some of you may know, you can define some skills or use some memories, right? Here, I'm not really using them to see you how it works, like out of the batch, right? So here it's searching through the available tools. So it can look at which tools are available and use them. And here it decided the way to go. So it's creating a sphere. So it's using the sphere tool to create one. So here it shows 0, 0 at the center and 25 millimeter radius. Make a TPMS lattice using the function. So it chooses a cell size of 12. And then that's interesting because the LM already have some like engineering knowledge, right? It knows that it needs to do an intersection to actually calculate the model. And here you can see my lattice sphere. And then I can just go on, right? So I can say apply 2 millimeter thickness and lattice sphere next to it. And here, so I don't really need to tell the LLM where to put the sphere, for example. So usually, if you would do this in a traditional way, you need to calculate the new center next to the sphere. So you need to figure out where to put it and then use a different lattice and do the thickness, etc. But here, because the LM is actually kind of intelligent, right? It will know that here first you need to apply some thickness, 2 millimeters that I've asked it, then make a second sphere next to it. So here you can see it offset the center by itself. So it chooses like the right center according to the radius. And then, applying a different pattern of lattice. So I didn't even ask it to apply different lattices, but it did it because it's kind of logical. And then, do the Boolean union to see both spheres next to each other. And hopefully, here, we can see like the two spheres here next to each other. So pretty interesting stuff. So of course, this is a really simple example, but you can do some actual engineering work with this, right? So for example, I've got that part on my PC, and I can just ask it to do some topology weaving on that part. So just to remind you, topology weaving is the alternative to topology optimization that we've made here at Cognitive Design. And it will try to apply the workflow on that part. So because I'm not using any skills, it's actually the MCP server that gives the context to the LLM. So there is some kind of user manual that is embedded to tell him, okay, if you want to optimize the part, then you need to do like this. If you need to convert, for example, your part from step to mesh, you need to use that function, etc., etc. So it did by itself. Here I didn't give some functional regions, but it extracted them, because to do topology weaving, you need these functional regions to actually connect them together. And here you can see it's estimating a resolution by getting the size of the model. So here it found 0.4 millimeters voxel size, and then it will go on with the workflow and show the functional regions and then apply the actual topology weaving on it. So again, this is a very simple example, but now, like, what gets interesting is you can actually work with it, kind of, and do some projects. And so, for example, I've tried to do, using that method, the workflow that Gregorio showed earlier during the webinar with the two brackets. And I was able actually to do it with really minimal inputs. So I just let it calculate the weaving. We can go back to it later, right? I've recorded it because we don't have enough time to show it you live, but took 20 minutes to generate a DOE on these brackets, and the input was actually pretty minimal. So the prompt was actually only this. So I give the path to the two models, and I just asked it to do a DOE for 3 processes, like Gregor was showing: IT manufacturing, machining, die casting. Use both topology optimization and topology weaving, and do a report using our branding. So I've got a skill set up in Claude to apply like the CDS branding to it. And for the load case part of it, it was actually a really simple description. Could be an Excel. Here I've used a text file, right? Where I described, okay, I've got a torque. The regime is 8 millimeters on the z-axis. Here's the direction. Here's the magnitude. And it's the same for the other bracket. So just with this, and what's really interesting here, you can see I've told it where the load is applied, but it needs to figure it out by himself, right? So here I just say it's fixed on the 3 surrounding holes. So you can see afterwards on the triangle bracket that there are 3 holes. And here I've said, okay, apply the force on the holes oriented in Z direction, and fix it on the X direction. And only with this input, and then I just launch it and go grab a coffee, right, and let it work. But yeah, it will try to figure out like what would be the best approach. So among the tools that we give it access through cognitive design, so you have some design operations, right, like topology optimization, topology weaving, lattices, etc. You have analysis. So this is the KPIs shown in the Design Explorers. So it can calculate these and make it access to it. And there is a tool also to use surface selection. So it can actually explore the part and find out with only like text input where it needs to apply the load cases. Yeah, so here you can see that it's deciding what kind of workflow to do it, right? I've just given minimal input, so it decides it, but I can also tell it what to do, right? It's even easier. And then it will load the 3D models. It will apply the load cases, right? So here you can see afterwards that it's listing all the holes to find out which one it needs to put the torques and the displacement. Then it creates the load cases. Yeah, you can see here that it was able to select the faces. So here are the 3 surrounding holes I was telling earlier. Yeah, and so all of this was done automatically using the MCP, and then it will run several topology optimization jobs, several topology weaving jobs, and then at the end apply the manufacturing driven design operations in order to make it for IC manufacturing or die casting, etc. And here you can see we can keep the human in the loop, right? So I've looked at some results and I say, okay, the support bracket is a little bit too thin. I don't like it. So it will just like work on it again, modify it and make another variation. So yeah, we're seeing some 3D models, but yeah, can show it to you at the end. So yeah, around 20 minutes to calculate all of this. A lot of the time, actually, the clone needs to compact the conversation to keep the context right. So this can take a little bit of time. And yeah, at the end, it creates a folder with all the 3D models and the images. And it created a report. So you can see the report here. So this was created automatically. You can either like create Word reports, HTML reports, whatever your LLM can do, right? Here, Claude is pretty flexible on this. And here you can see it made a scatter point graph with like each models and the KPIs. And there's a little bit of interactivity too. So here I can see, for example, this is the AM version. This is the molding version. That's the machining one. That's the reference, etc., etc. Yeah, and you have all the results here at the bottom. And yeah, I asked it also to put some insight about the methodology. So yeah, it's what we are exploring right now on the R&D side of CDS to do some orchestration of workflows.
Yes, thank you. So we can answer to some question to conclude this webinar. I saw that Henri already answered to a lot of them. So I see here the solver for topology optimization is not in-house, is powered by intact solution like the FEA simulation. But the topology weaving is our version, let's say.
Yeah, and it can work with commercial codes, of course. So you can export the models to simulate them in other softwares like ANSYS. Then you can import back the results. For example, if you want to do some simulation-driven design, so you can import the stress field from ANSYS, for example, to do the thickening, like Gregory was showing just before.
Yes.
Yeah. Okay. I see that Robert is asking for the canvas. Yeah, so definitely we can send you an image or the demo
Yeah.
file. Yeah, if you have a cognitive design license.
For the direction of CNC machining, actually, it's always X, Y, Z direction. So you have to orient the model.
Yeah, and you can choose the X, Y, and Z direction, so you can choose only one or more of them. Yeah. So another question. So is the MCP server running on a local machine? So yeah, it's actually running on my PC, and it can also work with local LLMs models, right? As long as your client supports the MCP connection. So yeah, it's something that we are exploring with some companies.
Yeah, for the simulation at the moment, yeah, we only have static loads, and we will, and at the moment it's only stress simulation, mechanical simulation, but we will add thermal and thermo-mechanical simulation with the next release.
Another question from David: do you work with voxel or implicits? So we actually use like true implicit representation of the functions, but we use Marshall cubes or voxels to like export them. But internally, like when you do the calculations, it's using sign distance fields, so implicit models. And another question. So is costing an active constraint in the design exploration as well? What about field data, correlation, fatigue? Yeah. So yeah, costing is a key KPI in the design exploration. So you have it directly inside the design explorer. So you can use it to do some DOEs and find out like what part would be the cheapest, for example. Yeah, and so right now, so there was also another questions on what type of KPIs. So for those interested, we can send more documentation about this. But right now, it's mainly 4 categories. So you have performance, where it's the static simulation results. So you have all the classics, right? Stress, displacement, strain, energy density, etc. So yeah, not yet fatigue, for example, but you could calculate it from the stress using Waller curve, for example. Yeah. And
okay, so.
And yeah, another question from Alexi. So are you planning for other physics? There are quite a few questions about this, by the way. So answering them all at once. So yeah, the next step will be to add thermal and thermomechanical static simulation. So this is upcoming soon, end of Q1. So we can share the roadmap. Yeah, sure, Alexi. Yeah, no plans for CFD yet short term, but we are looking into it. Okay. And another question from Daniel. Does CDS offer generative design capacity where you can generate geometries or part with prompts, or do you always have to start by importing from legacy CAD? So yeah, so right now you could actually make some simple designs, right, using primitives. So if you use, for example, the prompt-based approach, actually, like Claude, for example, can already do some basic text to CAD. So you could ask it to create a design space for you. But most of the use cases in cognitive design are better when you start from a design space. However, it doesn't. So if you have the legacy part and not a design space, for example, we can create the design space out of it.
Yeah.
So we have some functions to simplify a model, to fill in the gaps, for example, to make a bigger envelope out of it. You could also design parts only using functional regions, so the functional interfaces, so cylinders, hole, and all the connecting surfaces. So there is quite a lot of flexibility on that side.
Yes.
Another question, can we import CMX, NX file, PRT, PTC, etc.? So right now, we only support the general format, like step files. And for the meshes, there is a little bit more like STL, OBJ, 3MF. But it's in this year's roadmap to support more formats like CatPart, SolidWorks, etc.
Okay. Well, I think we can wrap the webinar up. If you still have other question, you can always contact us. You will have the access to the replay also. And yeah, so thank you everybody everybody who joined today for the webinar. And yes, see you next time.
Thanks everybody, and don't hesitate to contact us with the QR code.
Yes. Bye.
Thank you.